In this video, we're going to be looking at graphing absolute value functions as our sole objective. All right, so let's get right into an example. I would like to graph y equals the absolute value of x by making a table. Okay, I'm going to have 5 values in my table that I will plug in for x. -2, -1, 0, 1, and 2. Okay, the absolute value of -2 results in 2. Plot that point. The absolute value of -1 results in 1. The absolute value of 0 is 0. The absolute value of 1 is 1. The absolute value of 2 is 2. All right, so obviously we could plot more points, but I think you can see the trend here. What's happening is we're getting what I'll describe as a V for a graph. And a couple things to notice here. First of all, the graph is of a function. It passes the vertical line test. So absolute value graphs are functions. And the graph has a vertex associated with it, in this case at the origin. And there is symmetry in the graph across the y-axis that's passing through that origin or through that vertex, okay? The domain here is all real numbers, which I'm going to use both notations for. I'll let you choose which one you prefer. And then the range is anything 0 or larger. Okay, I should back up. In terms of domain, the fact that it's all real numbers, that's just telling us that we're able to plug any value we want in for x from the entire real number system. Okay? All right, now one other interesting thing to note here is that you can think of this absolute value graph as a piecewise function where one half of the v is coming off of a linear equation of y equals x, and then the other is coming off of a linear equation of y equals -x. So we could rewrite this as f of x equals positive x when x is greater than or equal to 0, and f of x equals -x when x is less than 0. So that's an interesting property. Piecewise functions are related to absolute value functions. Okay. All right, now I want to play around with the look of the absolute value equation, and I want to see how does this graph change of y equals the absolute value of x when I start manipulating the equation. Okay, so let's click over here to Desmos, get out of your writing tool, and we're going to look at functions of the form f of x equals a times the absolute value of x minus h added with k. And we want to know how does that graph that we just made, how does it change as the values of a, h, and k change? So let's look at this and investigate in Desmos. All right, so right now you have on your screen, you have the graph of y equals the absolute value of x, which we just did by hand, okay? And there's technically two graphs here that are represented with equations in box 1 and box 2, but right now they're representing the exact same equation, okay? Notice I have the slider for a set to 1, and h and k are both set to 0. So that means box 2 is technically y equals absolute value of x. All right. Now let's explore changing the value of a. As a gets larger, notice how the red curve is getting, we'll call it skinnier or narrower. And it's like the slope of each half of the lines that make up the V. It's like the slopes are increasing as A gets bigger. Okay. Now, what if I make A negative? Well, it changes the V from opening up to opening down. It's giving us a reflection across the x-axis here. Okay. As I keep making A smaller values that are negative, notice I'm having that narrowing effect again. Okay, so let's formalize that into our notes. We'll say that the A value controls a couple things for the graph. It controls the width, which is in this case a lot like the slope of each half of the V. And it controls direction that the V opens. Meaning up or down. Okay. Now let's look at the H and the K values next. Back here, I have A reset to 1, and let's just focus on the value of H. When H goes positive, it shifts the graph to the right, and when H is negative, it shifts the graph to the left. So H has a horizontal translating effect here. All right. What about K? K, the number that's being added outside of the absolute value, it's going to move the graph either up as K gets positive or down as K gets negative. Now, if you put H and K together, understand that as you move the graph up and down, left and right, it's moving all the points on the graph, but the one we want to focus on is the vertex. So like if I make H1 and I make K3, notice the vertex of this graph is at 1, 3. So that's pretty important to observe because it tells me that I can look at my equation and identify the vertex right away just by knowing the H and the K value. All right, so let's put those into our notes as well. We're going to say that H translates the graph left or right. And we'll say it controls the x coordinate of your vertex. And similarly, K translates your graph up or down. And controls the y coordinates, the y coordinate of your vertex. All right. So based on these observations, now let's do a few more examples, okay? Go to example 2 here, and we would like to graph the following two functions, all right? Let's start with the one that's over on the left. F of x equals the absolute value of x minus 3 added with 2. So based on what we just observed, I can look at this function and I can identify the vertex based off of these two numbers. The vertex is 3, 2. Okay, let's go ahead and plot that. And one thing I really want to make mention of here is that while it appears in the equation that 3 is negative, notice that when I list the coordinates of the vertex, I have that as positive 3. Okay, that may be something that we kind of skipped over in the Desmos investigation, but basically what I'm saying here is that if the number is being subtracted from x, you're actually going to use the positive of that number as the x coordinate of your vertex, okay? And if it were being added, you would be using the negative of that number, okay? Now, once I identify the vertex, I'm going to come up with a table of values centered around that vertex. So I'm going to put 3, 2 in the middle, since the vertex is literally the middle point of the graph. And I'll pick a couple values that are smaller than x, the x coordinate of that vertex, and a couple values that are larger. Okay. Now let's plug 1 in for x into the function and see what we get for y. 1 minus 3 is negative 2, but then don't forget to take the absolute value of it to give you positive 2. 2 plus 2 is 4. So we're plotting 1, 4. If I were to plug 2 in, 2 minus 3 is negative 1, the absolute value of which is 1. 1 plus 2 gives me 3. And then if I were to plug 4 in, 4 minus 3 is 1, absolute value of which is still 1. 1 plus 2 is also 3. Notice how those are equal? Not a coincidence. That tells me that I had the correct vertex, and it's showing the symmetry of the graph. By the same reasoning, when I plug 5 in for x, I should get 4 out for y. These two should be equal. Okay, and here we have our graph. I also want you to notice that as you move from the vertex to any of the other points, you're always going up 1 and right or left 1. And that's because of the fact that the a value in this particular equation is 1. Okay, I know to go up 1 from the vertex because of a being positive, and then you have to go both left and right 1 based on the nature of these being v's. Okay. All right, what is the domain of this graph? Well, again, domain for any absolute value function is all real numbers. And the range is going to be based on the fact that the graph opens up and its y-coordinate of the vertex is 2. So it's 2 up to infinity. Okay. Next example. This one I would say has a vertex of -1, -2. Okay. Plot that point. Another table of values. Put the -1, -2 in the center. Pick two values smaller than that x coordinate of the vertex and two values larger. If I were to plug -3 into the function, I'm going to add 1, which gives me -2, absolute value of which is 2. 2 times -2 is -4. -4 minus 2 gives me -6. And by symmetry, when I plug 1 in, I should get -6 out as well, right? These two should be equal. If I were to plug -2 in for x, -2 plus 1 is -1, absolute value of which is 1. 1 times -2 is -2, subtract it with 2, -4. By the same reasoning, that should be -4 as well. And there you have your graph. All right, couple things to notice here. This time the graph is opening down and it's a little bit narrower than the previous graph. That's because my a value in this case is -2, right? This number right here. And basically we can say that once we have that vertex, I need to go down 2 units and either left or right 1 unit to get to more points on the graph. Okay. Domain, all real numbers. And range, any number less than or equal to -2. All right, now it's your turn. You're going to pause the video. You're going to try to graph the function given in practice 1, and then come back and check your work with mine.